Hello, welcome to this another lecture of this course Computer Aided Power System Analysis. In the last lecture, we have looked at the basic procedure of the Newton-Raphson numerical method. Today, starting with this class, starting with this lecture as well as for the next few lectures, we would be discussing about how to apply this basic Newton-Raphson numerical method for the solution of the power flow equations. Now, as we have already indicated earlier, Newton-Raphson method is actually of two types. One is called the polar method, another is called the rectangular method. So, first let us try to understand what is meant by the polar method and what is meant by the rectangular method, and after that we will today start with the Newton-Raphson polar method. So, in polar method, now we have already discussed that our unknowns are actually unknowns for load flow, solution are actually complex voltage V I for all I is equal to 1, 2 to capital N, where N is the number of bus in the system. Now, because V I is a complex quantity, so then therefore, V I can be written as magnitude V I and angle theta I, and it also can be written as E I plus J F I, where E I is the real part and F I is the imaginary part. Of course, E I would be is equal to V I cos theta I and F I would be V I sin theta I. So, now what happens is that in the case of polar method, our unknowns are, so polar method our unknowns are V I and theta I, that is basically the magnitude and the angle. And in the rectangular method, our unknowns are E I and F I. So, then therefore, this is the only difference. So, then essentially in the case of the polar method, we do solve for the angles directly as well as also the voltage magnitudes. On the other hand, in the rectangular method, we do not solve for the voltage magnitude and the angle directly, we rather solve for the real and imaginary part of the voltages, and then afterwards from this real and imaginary part of the voltages, we do calculate the voltage magnitude and angles. Now, from today we would be actually starting with Newton-Raphson polar method. So, we start with Newton-Raphson load flow, we call it NRLF, in Newton-Raphson load flow in polar coordinate, we call it polar coordinate. Now, we know that our load flow equations are or rather power flow equations, we also call load flow or power flow equations are P I is equal to V I V k y I k cosine theta I minus theta k minus alpha I k, where k is equal to 1 to n. and Qi is equal to Vi Vk Yik sin theta I minus theta k minus alpha I k, k is equal to 1 to n. And we have already seen what are these quantities. For example, Yik is nothing but the magnitude of the element of the bus admittance matrix corresponding to the ith row and jth column, and alpha ik is the corresponding angle and pi and qi are the injected real power and the injected reactive power at bus I. Now, let us see that what is the total number of unknowns. So, to essentially understand that, we have to now first understand that what are the unknowns at different buses. Now, we have already discussed that there are three types of buses. So, there are three types of buses and these three types of buses, one is slack bus, one is PV bus, one is PQ bus. At slack bus, known are Vi and theta I, that is equal to 0. So, then unknown are actually nothing, nil, because we are only trying to solve for the voltage magnitude and angle at all the buses, and after that if we know these voltage magnitudes and angles at all the buses, we would be able to calculate anything and everything. So, then therefore, here we do not take that our unknown is Pi and Qi, rather we say that at how many buses voltage magnitude or angle or both are unknown. I mean, that is what we are now trying to see. At PV buses, we know that our known is Vi and Pi. So, then unknown would be theta I, and at PQ buses our specified quantities are Pi and Qi. So, therefore, my unknown would be Vi and theta I. Now, if I have got, as we have already said, we always say that there are n bus system, m generators, that is our convention. Bus 1 is slack, 2 to m are PV, and m plus 1 to m plus 2 to n are PQ. So, this is our convention. So, then therefore, theta I would be known. So, then therefore, here this theta I would be unknown for I is equal to 2 to m, and here Vi and theta I would be unknown for I is equal to m plus 1 to n. So, then in total theta I are unknown for theta I to be calculated for all I, if we do combine this, is equal to 2 to n, and Vi to be calculated for all I is equal to m plus 1 to n. So, then therefore, total number of unknown theta, total number of unknown theta is equal to n minus 1 here from here, and similarly total number of unknown Vi is equal to, it would be n minus m. So, it is n minus m. So, then therefore, total number of unknown is equal to n minus 1 plus n minus m is equal to 2n minus m. Now, we denote our unknown vectors as V. This is an unknown vector V, and this is actually the unknowns are V m plus 1, V m plus 2 dot 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 V n transpose. So, this would be an n minus m cross 1 vector, and theta, this is an unknown theta, this is theta 2, theta 3 up to theta n t transpose. So, it would be a column vector. So, it would be n minus 1 cross 1. Now, when we look at the expression of Pi, again I write it is Vi Vk Yik cos theta I minus theta k minus alpha ik, k is equal to 1 to n. So, we can see that in this expression of Pi, these quantities V m plus 1, V m plus 2, V n are already present, as well as theta 2, theta 3, theta n are also present. So, then therefore, any expression of Pi can be written as some function. We also call it, I mean, with an abuse of the convention, or rather with an abuse of the notation, we call it that Pi is a function of vector theta and vector v. Similarly, we can write down that Qi, which is k is equal to 1 to n Vi Vk Yik sin theta I minus theta k minus alpha ik. So, this also can be written as that it is also a vector of it is also an function of the unknown vectors theta and v. So, then therefore, each of this quantity is also a function of unknown vectors. Now, let us see. Now, what we have already said, that our total number of unknown is 2n minus m minus 1. So, now if we wish to solve for this total 2n minus m minus 1 unknown quantities, we also should have this many number of equations. So, now let us see from where we will get these many number of equations. Now, equations should be only found out only from the known quantities. Now, let us see that what are the known quantities. See the known quantities. What are the known quantities we have? We have Pi is known for all I is equal to 2 to m. So, this is for PV bus, and for Q bus and for PQ bus, Pi is known also for I is equal to m plus 1, m plus 2 to n, and Qi is also known for I is equal to m plus 1, m plus 2 to n. So, this is for PQ bus. So, here the number is m minus 1, here this number is n minus m, and here this number is n minus m. So, if I add them together, total comes out to be 2n minus m minus 1. So, then therefore, what we have got, that we have got total number of equations, that is total number of known quantities are is also 2n minus m minus 1, and also my total number of unknown quantities is also 2n minus m minus 1. So, then therefore, this is solvable. Now, the question is, how do I solve it? Now, we have said that Pi is actually a function of vector theta and vector v. So, then I can write down that Pi is a function of theta 2, theta 3 up to theta n, then Vm plus 1, Vm plus 2 to Vn. Similarly, Qi is also a function of this vector theta and vector v. So, I can write down, if I expand this, so this is a function of theta 2, theta 3 to theta n, Vm plus 1, Vm plus 2 to Vn. So, then what I have got? So, I have got these are my unknown quantities and these are my known quantities, sorry, and basically these are my unknown quantities. So, and these are my unknown quantities, and my equations, that is the functions, are known which are basically, or rather I do have some function which is a known value, which is basically the function of this unknown quantity. So, then therefore, it fits exactly into the basic framework of the Newton-Raphson numerical method. So, then what do I do? So, as usual, that we have to calculate the correction vector. Now, in actual practice, what we have, that Pi, which is a function of this vector theta and v, has got is equal to some value Pi specified, and Qi, which is also a function of this theta and v, vector v, is actually is equal to Qi specified, correct. For example, if I have a load bus, for example, let us say bus 5 is a load bus, and at that bus there is 100 megawatt real load and let us say 50 MVAr reactive load. So, then if I do take our base MVA to be 100 MVA, so then in that case what we will say, that my P5 specified would be equal to minus 1 per unit, and Q5 specified would be equal to minus 0.5 per unit. So, then therefore, these quantities would be known. Now, so then basically these are my equations. Now, if I do expand these equations, so then what do I get? So, applying Taylor series expansion, so now if I apply Taylor series expansion to all this, so what I get Pi specified is equal to Pi theta naught Pi v naught plus del Pi by del theta 2 into delta theta 2 plus del Pi plus del theta 3 into delta theta 3 dot del Pi by delta theta n into delta theta n plus del pi by del Vm plus 1 this equation would be for all I is equal to 2 to n, because we can see that pi would be actually specified for 2 to n. So, then if I apply this Taylor series expansion to this equation of pi, we get this, right, and theta 0 and v 0 are the initial conditions. Now, basically from where this equation comes? Basically this equation comes from the fact that we have got pi theta. So, this is the equation which is a vector of theta and v is equal to pi specified. So, then if I wish to solve for it, so then what I will get it? So, if I, so then obviously I do not know theta, I do not know v, so but I want to solve for them. So, then what I will do, that I will assume some value of theta naught and I will assume some value of v naught, and then I will actually basically calculate their correction vectors delta theta and delta v. So, that should be equal to pi specified. So, then therefore, from here what I will get is pi theta plus delta theta, so theta naught, and v naught plus delta v naught plus delta v should be equal to pi specified, and this term has been expanded through Taylor series. So, this term has been expanded through Taylor series. So, this is Taylor series, right. Similarly, we have equation is q I, which is a vector, which is a function of vector theta and vector v, that is equal to q I specified. So, then again I take some initial guess plus some correction, and I also take some initial guess here plus some correction, that would be equal to q I specified. So, now I do take, so now I again do take, I mean do actually perform the first order Taylor series expansion of this expression as we have done here. So, then if I do take, by taking Taylor series expansion, taking Taylor series expansion, taking Taylor series expansion, what we get? We get is that q I specified is equal to q I is a function of plus del q I del theta 2 into delta theta 2 plus del q I plus This would be for I is equal to m plus 1 to n, because we can see from here for q I varies from m plus 1 to n. So, then therefore, if I do collect all these equations together and do write them into a matrix form, so then what do I get? So, collecting all the above putting them in a matrix form, we get, what do I get? So, what do I get? We get something like this: del p2 by del theta 2, del p2 by del theta 3, dot 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 del p2 by del theta n, then del p2 by del Vm plus 1, dot 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 del p2 by del Vn. Then we do collect all these p's and we get del Pn by del theta 2, del Pn by del theta 3, del Pn by should be del theta n, then we get del Pn by del Vm plus 1, dot 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 del Pn by del Vn. Then start the Q then del q n by del V m plus 1, del q n by del V n, so this big matrix multiplied by delta theta 2, delta theta 3 up to delta theta n, then delta V m plus 1, delta V n, and this is P2 specified minus P2. Now, for our convenience, we term this Qi calculated. Qi calculated means, what is mean by Qi calculated? Qi calculated means that I do have expression of Qi, that is I mean Vi, Vk, Yik sin theta I minus theta k minus alpha ik. There in that expression I will substitute the values of theta naught and V naught, that is basically the initial guesses of all these thetas and all these V's, unknown V's, and of course we already know the I mean what the other values of theta are V, which are already known. So, we do substitute these values of initial theta and initial V, and then we calculate the value of Qi, that is basically we do get a numerical value of Qi. So then this expression we say for the purpose of convenience as Qi calculated. Similarly, this expression we also call as Pi calculated. Here also in that expression of Pi we do substitute the values of initial values of theta and initial values of V, and then after that we do get some numerical values of Pi. So, that is basically the calculated value of injected real and reactive power with the initial guess of angle and voltage, that is angle and voltage magnitude. So, we write it as P2 cal P3 SP minus P3 cal is P n specified minus P n calculated. Then we have Q m plus 1 specified minus Q m plus 1 calculated, and then similarly Q n specified minus Q n calculated. So, this is what we get. So, then we have got a big matrix here, big vector here, big vector here. So, now let us partition them. So, now what we get is we partition this big matrix like this. And we also partition this vector like this, and we also partition this vector like this. This matrix we call as del p by del theta matrix. So, we call it this matrix. So, this is the matrix J1, we call it this matrix J2, we call this matrix J3, we call this matrix J4. This is a vector, we call this vector as delta theta vector. This is a vector, we call it delta V vector. This is a vector, this vector we call as delta P vector, and this is a vector we call as delta Q vector, Q bar vector. So, then therefore, with this terminology, this entire matrix, big matrix, can be written as more succinctly as matrix J1, matrix J2, matrix J3, matrix J4, then delta theta vector, delta V vector is equal to delta P vector is equal to and delta Q vector. So, in this lecture what we have done, we have first discussed what is meant by Newton-Raphson polar and rectangular method, and then after that we have specified that what are the unknown quantities for Newton-Raphson polar technique, and as well as the what are the equations for this Newton-Raphson polar technique, and subsequently we have linearized them by following the basic procedure of Newton-Raphson numerical method. And by doing so, and after doing so, and after collecting all these equations together, we have arrived at this succinct matrix equation. So, in the next lecture and onwards, we will be looking into the more details of this matrix equation. Thank you.